Hi everyone, Mary here, and let's talk this time about wave interference. Now here's a question for you. Can two pieces of matter be in the same place at the same time? Well, you and I both know that if something is full, you can't add anything more to it. It happens with glasses of milk. If it's full of milk and you try and fill it up with orange juice, you're just going to end up with a mess. That's just a rule of matter. But what about waves? Can two or more waves be in the same place at the same time? So can you be streaming music and texting at the same time, which means your cell phone is collecting two different wave signals? Can you be in a situation where you have two people talking and you can differentiate one person's voice from another? Can you be out in the woods and you can hear a bird song and you can see the bird at the same time? And right now, if you take a moment, can you hear two sounds at once? Maybe you're listening to my voice and in the background there's a car on the road, or you can hear your furnace or a fan running, or you can hear a distant conversation in another room. So here's the weird and crazy thing about waves. Waves can be more than one of them in the same place at the same time. And that is called the principle of superposition. Here's what it says. Two or more of the same type of waves, light, sound, water waves, can be in the same place at the same time. But when the two or more waves are in the same place, their amplitudes momentarily add up, and then the wave moves on unchanged. So let's draw this out and see how this works. Let's say I have two waves, wave A and wave B, and they're coming towards each other in two different directions. As they get closer and closer and closer, they will get to a point where I have wave A and I have wave B that are in the same place. When they are there, their two amplitudes algebraically add. So I end up for a brief instant with an amplitude that is bigger than A and bigger than B. After that instant, A continues to move in its original direction, B continues to move in its direction, and it acts as if nothing ever happened. They just had this brief encounter where they mingled for a moment. Now, what this provides in waves is something which is called constructive interference. This is when you have two waves that add up and produces a wave with a larger amplitude. The two waves move towards each other, they produce a bigger amplitude, but it's just for an instant, and then the wave pulses move on as if nothing occurs. This is referred to in the lingo of waves of being in phase. Now, this produces some weird and wacky wave effects. One of them is that you can add sound to sound and get louder sound. Let's say you are an audiophile. You are someone who really loves music, loves listening to music, and you produce a music room designed so that you can sit and you can listen to your music. Someone who sets up a room like this positions their individual speakers, and they position where they're going to sit and listen to the speakers, understanding about constructive interference, that each speaker is going to produce sound waves, and those sound waves are going to produce places where the compressions are going to add up and places where the rarefactions can add up. And they're going to make sure that they are sitting in a location where they are going to get the highest quality sound. They're not going to want to be in a spot where the rarefactions add and the sound wave basically nullifies and you end up with no sound. It's going to sound terrible. So these locations of where you sit and listen to the music is very, very important. Constructive interference also occurs with light. You can add light to light and get a brighter light. And this is what occurs when someone makes a laser. Laser is actually an acronym. An acronym is where you take the first letter of a bunch of different words and you make another word out of it. Laser stands for light amplification by stimulated emission of radiation. So what occurs in a laser is it has a lasing cavity. This can be a chamber of gas. This can be a small solid material. If you have a solid state laser, there is a mirror on each end. One of them is a perfectly silvered mirror and one is a partially silvered mirror. What happens is light is stimulated. So something causes a whole bunch of different atoms inside of the lasing material to be excited. So electrons get excited to a higher energy state, and you have a whole bunch of these electrons that are excited to high energy state inside of the lasing material. Randomly, one of the electrons falls, and when the electron falls, it marches down the laser. When it hits another atom, it will cause the next the next electron to fall. And when the next electron falls, instead of having just one photon of light marching down the lasing cavity, you now have two photons in phase, crest over crest, trough over trough. These march down, hit another electron, and you now have three in phase. Well, when they add up in phase, you are producing a wave with a much bigger amplitude. And if you recall, amplitude is related to energy. And more energy means that you can do things like cut through solid steel or use a laser to cauterize or do surgery. And you're producing simple old light that is very, very powerful. This process goes up and down the lasing cavity until there is a small opening in the laser. Some of this laser light escapes, and that is actually your laser beam. But none of this would be possible without constructive interference and light being added to light to produce a brighter, more coherent, added amplitude light. Now you also can get destructive interference. Destructive interference is when waves add to produce a smaller amplitude. So let's say I have wave A and wave B that are approaching each other. And at the instant they meet, wave A is a positive amplitude, wave B is a negative amplitude, and when they algebraically add, their amplitudes nullify. They equal zero. If it perfectly equals zero, it's called being 100% out of phase, and you go from wave energy to nothing, and you can have complete cancellation of the wave energy. Now this happens at the one location or moment when the waves are canceling each other. After that close encounter, wave A goes on unscathed and wave B goes on as if nothing occurs. This is called destructive interference, and it means you can have sound plus sound giving you quiet. Now, the classic place that this is seen in modern times is noise-canceling headphones. These are used by people who are involved in shooting sports. Many of you might have them for listening to your music. And what occurs in noise-canceling headphones is the headphones themselves have within them a small speaker, and they are detecting background noise. Now, the background noise might be the hum of a radiator, it might be an engine, it might be traffic noise, and what it does is it takes those background noises, produces a signal within the headphones themselves that is 180 degrees out of phase, exactly opposite to the signal it's hearing, and it broadcasts that to your ears. When your ears has the background noise plus this 180 degrees out of phase signal, and it hears both of them, the two wave energies nullify each other. So it cancels out this background noise, and what do you hear? You hear your music. You do not hear the excessive noise from your sports, and it actually protects hearing by adding more noise to it. Weird and crazy stuff. Here's the other weird one. With destructive interference, it's possible to add light to light and get darkness. Yeah, I know. Doesn't that sound wacky? But if you take a light source and you take that light and you pass it through two tiny, tiny, tiny little slits, you can get what is referred to as an interference pattern, interference pattern of light. And this was first done about 150 years ago by a gentleman named Thomas Young, an Englishman. And what he found is there were areas of bright bands, dark bands, bright bands, dark bands. And these bright and dark bands were due to light waves adding up and canceling, adding up and canceling. Now, this is hard to see, but you can see it for yourself, and this is how you can do it. This is a picture of my fingers. Hold your thumb and your forefinger very, very close together, closer than I show here, and hold this very close to your eye. So if here's your eye, hold your fingers really, really close to your eye, like less than an inch from your eye. And get these two so they're closer, 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 so they're almost touching. And look between your thumb and your forefinger. Be in a dimly lit room, and then look at something that is bright, like a bright white wall, or something that is kind of plain, so it doesn't have a lot of pattern on it. And if you look between your fingers, what you're going to see, and it will be black and white, you're going to see something that looks very much like a barcode right between your little fingers. And what you're seeing is the light, as it gets squeezed through your fingers, is going to be interfered. The light waves will interfere with themselves and produce an interference pattern similar to the interference pattern seen by Thomas Young 150 years ago. You're actually seeing light plus dark, light plus light giving you dark. So cool. So very, very cool. All right, that will do for interference, and we'll see you later. Bye-bye.